Hi, let's discuss how to add finite decimals. So here I have two finite decimals written, 2.34 and 3.2, and we ask how do we add them? Well, recall from our definition that a finite decimal is in fact a decimal fraction. So 2.34 is a fraction and 3.2 is also a fraction. So since we already know how to add fractions, in some sense we already know how to add two finite decimals. So it's just a matter of pushing that idea through and figuring out how to get our final answer. So let's look at what I have here for you. So I have 2.34 plus 3.2 equals, and I keep the 2.34, and instead of 3.2 I do a little adjusting and I write 3.20. So in other words, I've attached an extra zero to the very right end of this finite decimal. So why did I do that? And so let me discuss the next step, and then I'll come back and I'll explain to you what I was thinking ahead of time. So 2.34, when we convert it into a decimal fraction, when we rewrite it as a decimal fraction by definition, it's really 234 over 100. So in other words, this is just a name for 234 over 100. Similarly, let's look at 3.2. If I hadn't attached that zero, and if I rewrote 3.2 as a decimal fraction, I would be getting 32 over 10, and then I would have to add these two fractions with unlike denominators. So instead I think ahead of time, and I think if I decide to put an extra zero, and I chose to add just one extra zero and in particular to this one, because thinking ahead, I would like both of my finite decimals to have the same number of decimal digits. So that way, when I convert each of those finite decimals into decimal fractions, I would naturally have the same power of 10 in the denominator. So this finite decimals has two decimal digits. This one has only one decimal digit, so that's why I decide to put an extra zero here. And in another video, we justified that adding these extra zeros to the very right end of the finite decimal doesn't change the finite decimal, and that is when we show our math reasoning was really by fundamental fact about equivalent fractions. So in any case, now here we are. We need to add these two decimal fractions. They have the same denominator, same 100. So adding them is very easy. The sum is another fraction, another decimal fraction, with 100 in the denominator, and the numerator is just adding 234 and 320, just adding two whole numbers, which is very easy to do. And we do that and we get 554 over 100. We convert it back into decimal and we get 5.54. So what we are really saying is 2.34 plus 3.2 is the finite decimal 5.54. So you might look at this reasoning and ask, is there a quicker way to get this 5.54? These steps contain all of the reasoning that justifies getting this answer. So now I'm going to show you an algorithm for adding finite decimals, and that's a quicker way of getting the answer. And when I show you the algorithm, I'll also explain to you how the mathematical reasoning of these steps is naturally packed into this algorithm. So let me go over the algorithm steps. They're very easy. Write your finite decimals, 2.34 and 3.2, and write them in such a way that the decimal points are lined up. So which is why, so in order to line up the decimal point of 3.2 with the 2.34's decimal point, I'll have to write the 3 underneath this 2 and this 2 underneath this 3. Here, there is nothing when I do line up the decimal points. And then after that, pretend like you don't have any decimal point and add up. And then finally, whatever answer you get here, then look at the decimal points that you lined up and right underneath it, put a decimal point, and you will get the correct answer. Why does this algorithm work? Why does it always give the correct answer? So I'll explain the reasoning in the context of this particular example, but you can carry over this reasoning to another example, and you see that this algorithm will work in another situation too. So let's look at what we've done here. So here, you remember me saying that because in this step I would like to have the same denominators and in fact same power of 10 as the denominator, I take the I adjust the finite decimal, which has the fewer decimal digits than the other one, and I adjust it by adding some extra zeros. So here I had to add an extra zero. So now that way this finite decimal has 2 decimal digits, this finite decimal has 2 decimal digits. That's exactly what's going on when I line up the decimal digits. Naturally, not having anything is like having the 0 here. Next, what do? We rewrite both of them as decimal fractions. They'll have the same power of 10 in the denominator. And then we're just adding these whole numbers. When I say pretend like you don't see the decimal point and just add, that's exactly what's going on. Having nothing here is like a 0. So when you're carrying out your addition, you're really doing just like this addition, 234 plus 320. That's really what you're getting. And once you get this, I say put back the decimal, line it up. Well, that lining up is exactly happening. Here, remember, this 100 came from these 2 decimal digits. And now the number of decimal digits is being kept track by this 100 until you reach this step and you say, I'm going to put back the decimal point in such a way that now the decimal point keeps track of this power of 10. Now, in this algorithm, all that's taking place, you don't need this denominator of 100 to keep track of the decimal point. If you line up the decimals, and after you add, you say put the decimal point in the final answer to line up with those, everything will work out just fine. So that's the reasoning for this algorithm. And so make sure you understand the reasoning that goes on, that in fact, firstly, adding a finite decimal is something that you already know if you know how to add fractions, and if you recall the definition that a finite decimal is a decimal fraction, you already actually know how to add to finite decimal. So this algorithm is only a quicker way of adding it, and like I said, the logic of why this works is explained by this long way. Thank you.